Jai Hind everyone, myself Sandeep Yadav, currently working as Assistant Professor in Department of Computer Science and Engineering. Today I am going to deliver a lecture on Concurrency Control Technique, which is part of the subject DBMS, that is Database Management System, whose AKG code is cases 501. It is an essential subject of computer science. Now, today we are going to learn different measures and techniques that are available in concurrency. So before discussing this technique, we must know what is concurrency. Concurrency is that we are able to make use of several competing processes at same moment of time without any conflict between the different participating transactions, so that the property of isolation is maintained properly, data remains consistent, the data is integrated. Integrity means that the state of the data must remain consistent. Now, following are the outlines in our lecture. First, we shall discuss what is concurrency. Second, we will be discussing various problems that are associated with the concurrency. Third, we are going to discuss locking protocol that is used in concurrency control. Next, we are going to discuss two-phase locking protocol. Thereafter, we shall be discussing one more additional concurrency control technique, that is time stamping technique. Later on, we shall be discussing deadlock. In addition to these techniques, we have some more techniques regarding concurrency control, that is, we have multi-version time stamping protocol, we have multiple granularity protocol, and graph-based protocol. So, first, we shall be discussing about what is concurrency control, why do we require concurrency control at all, and where we have to implement this concurrency control. So, first of all, we will be discussing what is concurrency control. Well, concurrency is the ability of any database to allow more than one user to access the data at same moment of time. See, in database, there are two types of execution. First type of execution is serial execution. First type is serial, and second is concurrent. So, serial execution is fine, but the problem is that at a time only one process will be executed, means the CPU will not be utilized properly. Second, the throughput of the system is quite low. Third, the waiting time for the transition increases because now the transitions are being executed one at a time. So generally the waiting time decreases. So in order to overcome these problems, we require concurrent execution, whereby we are going to make use of increased CPU utilization. Second, as the CPU utilization will increase, so the throughput will also increase. Next, the waiting time for the transitions shall also decrease. Now, no longer a short duration transition has to wait for hours for a longer duration transition to complete. So, that is a very big problem that is associated with the serial transitions. These problems are resolved through concurrent execution of the transactions. So, these are some of the few advantages of the concurrent execution. Now, there are three main problems that are associated with the concurrency. First is lost update problem, second is dirty read, and third is incorrect retrieval problem. These three are the main classical problems that are associated with the concurrency control, and all of these are covered in the standard textbook defined by different authors like Coates, Nawate, and Tate. So we will be studying them one by one. First is lost update problem. Now, lost update problem indicates that if two transitions T1 and T2 both read the same data item and update it, then the effect of first update will be overwritten by the second update. In this particular example, as we are going to see, is that there are two updates. One update that is done by this transition T1, this update. This is the update by transition T1. Now this update is lost by this particular transaction T2. So this is lost update problem. Now how we can avoid this problem? Without avoiding this problem, our transaction will not be properly finished. So how to avoid it? As it is already explained here, that the transaction T2 must not update the data item unless transaction T1 can commit data item. That is, first this transaction T1 that is updating the value of this data item X, then first this transaction will commit it. First it will perform commit operation, then only then transaction T2 should update this data item X, otherwise the inconsistency problem will be occurring. The next problem is dirty read problem, and the name itself suggests that dirty read means that we are reading a wrong value. The dirty read problem arises when one particular transaction updates some value and then that particular transaction fails due to certain reasons. Then the updated value is retrieved by the another transaction before it is changed back to the original value. So that particular transaction has read a wrong value. So how to overcome this? First we shall see what is dirty read. See, in this particular case, as we are seeing, this value of X, its initial value of X is 100. Then there are two transactions T1 and T2. Now at time T1, that particular value of X is updated and that updated value is now 50. Now this updated value is read by another transaction T1. Now T1 reads that particular value 50, then it completes its execution and commits. Now after that the transaction T2 fails due to certain reasons and decide to roll back it. Now after rollbacking the transaction T2, the value of X will be 100. This means that this transaction that has read the value 50, that value is incorrect value. Now that is a very major problem that we face in database. So all of these problems need to be avoided. How we can avoid? We can use various concurrency control techniques that we can avoid this particular type of situation. Now how we are avoiding it? A transaction T1 must not read the data item X until the transaction has committed the value. Now the problem here occurs is because we have read the value that is written by T2. Now that transaction T2 has not committed the value yet and it fails. So that value that is read by transaction T1 is 30. So what should happen is that if a transaction is reading a value from another transaction, then that value must be first committed, so that the value from the committed operations or committed transactions are only read, so that we can avoid the problem of dirty read. Next, we are going to study certain measures as how to maintain the concurrency control. See, concurrency control is desired in order to control the interaction between several of the transactions that are executing parallelly to each other in concurrent fashion. So why do we require this mechanism at all? Is that it is necessary to maintain the property of consistency, integrity and isolation of transitions so that the database remain consistent. So first technique that we are going to study is locking. See, in our general life, all of us are aware of the concept of lock. We lock our room, we lock our houses. Why? So that it is only used by us, other people are not able to use it. Whosoever has the key of the lock, that person will be accessing that particular house or that particular almirah. Same analogy is being used here in DBMS also. Here the concept of lock is associated with data item. to control access to that particular data item. So whosoever applies the lock can only access the data item. Other transactions that are running parallelly are not able to access the data item, so that the clash do not occur, the instructions do not conflict with each others. Now clearly we are seeing different users are there. There are 4 users. There are lock variables. See, if one of the user is accessing the data item, then another users are not able to access it. Otherwise, there will be conflict. So locking is a mechanism that is used to prevent concurrent access of data. Now, in locking protocol, a data item can be locked in 2 particular modes. First is shared mode, that is denoted by the word S. Here we can just read the data item, but we cannot write that, and that is denoted by the alphabet, capital alphabet S. Second mode is exclusive mode. When we take this lock, we can read as well as we can write a particular item. For example, if you want to update the value of a particular data item X, then we are going to apply exclusive lock. And if we are requiring just only reading a particular value, for example, consider that we want to know the balance in our account. So in order to know the balance in our account, we need only the read operations. In that particular operations, we will be only requiring shared lock, so that we are able to read the value. Now second is exclusive lock, where we withdraw the amount from ATM. When we withdraw the amount from the ATM, then the balance in our account changes. Then in that particular situation, we have to use the exclusive lock. Now there is low compatibility matrix. Suppose there are 2 transitions T1 and T2, and T1 has applied a shared lock on a particular data item X, and another transition T2 also want to apply shared lock. Then whether that transition can apply a shared lock or not. See, in concurrency control techniques of locking, any process or the transition that want to apply the lock, it has to first send the request for locking to the lock manager. The lock manager decide whether to accept the request or not, based on the condition that whether the data item is free or not, or second, if it is in lock mode, then it is in compatible mode or not. So it is the responsibility of the lock manager to grant the lock, and the permission is being sought from the lock manager. Now here we are seeing that if we are having the shared lock on a particular data item, and another transition T1, another transition T2 in this particular case want to apply the shared lock, then that shared lock is granted, because shared lock only involves read operation, and when both of the instructions are read, then no conflict occurs. So since no conflicting is occurring, therefore both of the mode are compatible and the permission is given by the lock manager. Now second analogy is when there is a exclusive lock on the particular data item by transition T1, and transition T2 wants a shared lock on that. So should we allow the transition T2 to have the shared lock to read the value? No, we cannot allow that particular condition, because the transition is performing the write operation already, and the values that it is writing are in transition. So we cannot allow any other transition to read those values that are in transition, otherwise we will be fetching incorrect value. So that lock is also not compatible. Now second row is when the other transition T2 want to apply exclusive lock on data item that is either in shared lock or in exclusive lock. So how? If the transition T1 has a shared lock on particular data item and T2 wants an exclusive lock, so wants a shared lock, then exclusive lock, then that is also not allowed. Now if the data item is already in exclusive lock and other transition also wants the exclusive lock, then that is also not allowed. So the gist is that if any one of the instruction is right, that is, if there is any one of the instruction is right operation, then another transition cannot be allowed lock. See, if one of the instruction is right operation, any one of the instruction is right, operation, then the conflicts occurs. So these things are bound to cause conflicts. That is why the modes are not compatible and we cannot allow these modes. So only there is one true condition, that is shared state. Rest are the false condition. This matrix is known as low compatible matrix. Now a transition may be granted lock if it is not in compatible mode. And if a transition, a lock cannot be granted, then the requested transition has to wait till all the incompatible locks held by the other transitions are released. Only then that is granted. Any number of transitions can hold shared lock on any data item. But if a transition holds an exclusive lock on the item, no other transition can hold any lock on that particular data item. Now this locking protocol divides the transition execution phase in three parts. When a transition starts executing, we create a list of data items on which we need locks and request the system for all the locks that our system requires. So this time lock acquisition phase is there, where the transition acquires all the locks and no other lock is required. Transition will keep its execution. Thereafter, as soon as the transition releases its first lock, the third phase is starting. That is, a transition will no longer requiring any lock, but it will only be releasing lock. So all of these three conditions are specified here. Here the lock acquisition is starting. In this particular portion, the transition will execute, and after the completion of execution, when we no longer require those data items, then we will starting releasing the locks. Now this particular locking protocol is also not deadlock free. This protocol also is not deadlock free. So we need some another mechanism where it is deadlock free. Now another variation of this particular protocol is two-phase locking, whereby we have two phases. First is growing phases and second is shrinking phases. Now growing phase is towards the beginning of the transaction, whereby we requires lock. We obtain the lock, but we don't release any lock. Now when a transition takes the final lock, then it is called lock point. Now second phase is shrinking phase, whereby it is, as already seen in the diagram, it is towards the end of the transition. Here the transition will be releasing the lock, but it will not obtain any lock. The transition enters the shrinking phase as soon as it releases the first lock after crossing the lock point. Now this locking, two-phase locking, is itself of two main categories. First is strict two-phase locking, second is rigorous two-phase locking. Let us see what is the difference between these two particular modes of locking. Now, in strict two-phase locking, a transition may release all the shared locks after the lock point has been reached, but it cannot release any exclusive lock until the transition commits or the rollback. The very purpose of these techniques is we want to avoid cascading failure. So in order to avoid the cascading failure, we have this implementation strict as well as the rigorous. So we will be releasing shared locks, but we will not be releasing the exclusive lock until the transition commits. The shared lock, the reason for releasing the shared lock is that shared lock do not alter the value or change the value of data item. That is why it does not cause any difference. So we can release that shared locks. Now it is more easy to implement this strict two-phase locking as compared to rigorous two-phase locking. Next, it ensures that if data is being modified by one transition, then the other transition read it until the first transition commits. This protocol solves the dirty read problem that we have studied in the beginning of this particular lecture. What is the problem of dirty read? Next is rigorous two-phase locking. In this protocol, a transition is allowed to release any lock. Either is not allowed to release any lock, either shared or exclusive, until that particular transition commits. That is, this protocol is more difficult as compared to the strict two-phase locking. That is because here we are not even allowed to release the shared lock. That is the reason that we follow strict two-phase locking more as compared to the rigorous two-phase locking. Now this protocol means that the transition, until the transition commit, no transition can acquire even a shared lock on data item on which the uncommitted transition has shared lock. Now this lowers the degree of concurrency. An important disadvantage that is arising because of these protocols are that we are lowering the degree of concurrency, thereby reducing the CPU utilization. So we must have some trade-off. Either we want higher concurrency or lower concurrency. So we need to keep all these things in the mind while we are dealing with these situations. Now next protocol, very important protocol, is time stamping protocol. As we have seen in this previous protocol of locking, we have the problem of deadlock. That is, the deadlock problem is occurring. So in order to that problem, we will be using the time stamping protocol, whereby each transition is being given a unique timestamp value, and that timestamp value is generally implemented using system or a logical counter. Now each transition has a timestamp associated with it, and the ordering is determined by the age of the transition. If there are two transitions, one that enter the system at 11 o'clock, then this is the timestamp value of that particular transition. The timestamping of another particular transition may be 11:05. Now transition T2 is an younger transition and T1 is a older transition. So the very purpose of having this timestamp value is that whenever the conflict occurs in system, whether a transition can perform the read operation or write operation, the conflict is resolved with the help of timestamp value. That is, it determines whether the transition is old or young, so that we are able to determine if the transition is too late in performing its desired operations. If the transition is too late in performing its desired operations, then we need to roll back that particular transitions so that the database remains smooth. Now the time stamping is denoted by TSTI. Now each data item is having read timestamp as well as each data item is having the write timestamp. Whenever the data item is read, it has associated value read timestamp, and whenever it is write, then it is the write timestamp value. It must be the largest timestamp of all those things. Now let us see how this time stamping protocol works. Suppose a transition T1 Ti wants a read operation. Now we have to just compare whether the timestamp value of that particular transition is less than write timestamp value. That is, the transition that want to read the value is an older transition. A younger transition has already wrote that value, so there is no need to perform the read because that value has been already lost. Second condition is the transition is a younger transition as compared to the transition that wrote the value, so that particular operation shall be successful. Now second condition is if a transition Ti issues write X operation, so whether that operation will be successful or not is again determined by comparing the various timestamp value. Now if TS Ti is less than the read timestamp value, then the operations shall be rejected as already a younger transition has read a value and this is not at all required. Again the operation will be rolled back in second condition also because this value is larger as compared to the timestamp value. That means younger values are larger, so naturally it will be rejected. Now the last condition is when TS is greater than equal to write timestamp value, then the operation shall be successful. Now this is all about the timestamp value. Now this transaction, this has an important advantage that this protocol is deadlock free. So this protocol is very important protocol, and generally this protocol is being asked in examinations. So in nutshell, in today's lecture we have studied two very important concepts. One is locking and second is time stamping protocol. Now the references that we have used is Navathe as well as Date books we have been using for this whole lecture, and thank you everyone for keep listening to me.